right, welcome back. You guys, we're going to take a look at derivative as rates of change. So if we interpret, if you remember the difference quotient, if this is our average rate of change, in other words, we're going from, oops, that would be the slope of the secant there in red, right? But once we run so that's our average rate of change of the interval from x to x plus h. But once we run that limiting process, limit as h goes to 0, then that will give us the instantaneous rate of change, so the f prime at x, right? And so to give you a little bit of background with this, if you remember that distance equals rate times time, in other words, your rate is your distance over time, then your average velocity would be the change in position or change in distance. I'm going to use s over your change in time. And so if you run the limiting process on that. If you run the limiting process on that, and what you would do is you would actually use the alternative form of the derivative to run that limiting process on that. Then the velocity ends up being the derivative of the position. You know, this is like feet per second, right? So the velocity is the derivative of position, right? If you were to run the limiting on that. Let me erase that and I'll come back over here to the table here for a second. So position, like if you had units, would be like feet. The derivative of position is velocity, so that would be like feet per second. Okay. And if you run the derivative of velocity, you get acceleration. Your units would be like feet per second squared type of deal. Okay. So let's take this position function here. S of t is being our position. Let's go ahead and find the velocity. So the velocity would be the derivative of position. 4 stays there. We run the derivative of t squared power rule. 2t to the 1 minus derivative of t is 1. Derivative constant is 0. So the velocity is 8t minus 1. There's our velocity function. And so our acceleration would be the derivative of that velocity, which is the second derivative of position. So now we take the derivative of 8t, so 8 times 1 minus the constant. So the acceleration is just 8. So if this had units on it, it'd be like 8 feet per second squared. Let's do an example where we throw an object vertically upward, and we've got this, it's given by this function, negative 16t squared plus 100. In fact, let me kind of give you, so this object's thrown vertically upward, right? T being 0, it's on the ground. This is my position function. S of t equals negative 16t squared plus 100. It says find the velocity of the object after 3 seconds. Well, to find the velocity, we've got to take the derivative. So negative 16 stays there. Take the derivative t squared, 2t to the 1 plus 0. So the velocity function is negative 32t. And so we want to find the velocity after 3 seconds. So again, negative 32 times 3, which is negative 96. And this is in feet in seconds, so it'll be feet per second. Okay, so another way to say, well, visually, this is saying velocity has magnitude and direction. Magnitude meaning how fast it's going. Direction meaning, like in this case, up or down. So this is saying at 3 seconds, like maybe this 3 seconds like over here, this object's like going down right there, 96 feet per second at that point. Now, that's like the position function, right? But I'm just saying, I haven't graphed the velocity function. But it's just saying this thing's going down that fast, 96 feet per second. And by the way, speed is just the absolute value of velocity. So the speed of this, so velocity, that negative is saying is going down, right? Velocity is saying is going down. So the speed is just 96 feet per second, right? Speed is directionless. That's what we're saying, right? It's going 96 feet per second, but velocity is telling us that it's going down. On this one, we've got a position function as well, and over an interval. And we're going to find the body's displacement. So what do I mean by displacement? That's just its change in position is all that is. What's its change in position? Like if it goes from like 0 feet out to 10 feet, it had a change of 10 feet, right? So we're going from on this interval. This is our t interval from 0 seconds to 3 seconds. So all we want to do is find s of 3 and subtract it from s of 0. Okay, so let's go to the side here. S of t to the 4 over 4 minus t cubed minus t squared, s of 3. Oops, that's a squared right there. Squared. Sorry about that. So we got 9/4. This is in meters. Plug in 0 now. So I got 0 to the 4 over 4 minus 0 cubed plus 0 squared. It looks like that is 0 meters. And let's do the displacement. So the displacement or the change in position would be s of 3, 9/4 meters minus s of 0, 0 meters. So it has a total displacement or total change in position of just 9/4 or 2.25 meters. That's your displacement. It also wants the average of velocity. Well, average is not instantaneous. This is not taking the derivative. Let me get a little room here. Remember how I said, rate or the speed here is distance over time. So average rate or average velocity would be the change in position over the change in time, right? In other words, the average, again, average velocity would be the change in position, so s of 3 minus s of 0, all over 3 minus 0, the change in time in seconds. This will be in feet. This will be in seconds. So what we're doing is we're just finding the average rate of change, if you will, right? We're not finding the derivative. We're just finding the average velocity. You're finding the slope is what you're doing, right? We're finding the slope. Well, we found s of 3, it was 9/4. S of 0 was 0, and then over 3 minus 0, which is 3. So we just end up with 9/12 or 3/4. Now this is meters, that's seconds. This is meters per second. So average velocity here is 3/4 meters per second. 0.75 meters per second is your average velocity. Okay. Now let's go ahead and find the speed. Now I mentioned that the speed is just the absolute value of the velocity. So let's go ahead and find the velocity function. Here's our position function. It's 1/4 t to the 4th minus t cubed plus t squared. let's go ahead and find the velocity, which is the derivative of position. So 1/4, take derivative t to the fourth, 4t cubed minus 3t squared plus 2t to the 1. So our velocity is t cubed minus 3t squared plus 2t, right? There's our velocity, and I want the velocity at the end points. So at 0 seconds, right? So here's the velocity, but let's find it at 0 seconds. So 0, and this will be in feet per second. Or I'm sorry, this is meters per second. Meters per second. That's at one endpoint. Now let's plug in at 3. So I got 3 cubed. And that'll end up being 6 meters per second. Okay. Now we also want the acceleration at the endpoints. Well, if here's our velocity function right here. So to find acceleration, I'm going to have to take that derivative of v of t. So t cubed, that's 3t squared, minus 3t squared, so minus 6t plus 2. There's our acceleration function. Find it at the endpoint, so at 0. Acceleration at 0 seconds is 2. This will be in meters per second squared. Remember, position's meters, velocity would be meters per second, acceleration would be meters per second squared, right? And then I want to find the acceleration also at 3. So I'd have 3 times 3 squared minus 6 times 3 plus 2. So I got 27 minus 18 plus 2. I got 11. Looks like meters per second squared. So there's our acceleration at the end points right there. And I should have mentioned here with my velocities, remember the velocity at 0 is 0 meters per second. Velocity at 3 seconds, so that's at speed as well, right? Speed is, and this one's a positive 6. If it would have been a negative 6, my speed would have still been 6, right? Because you want to take the absolute value of negative 6. But it's just a positive 6, so it's still your speed. Just remember that when they're asking for speed, they're asking for the absolute value of that number. So if it's negative, make sure you take the negative off, all right? So they ask you about speed there. All right, now, when, if ever, does the interval change direction? Well, for a body to change direction, first you've got to come to rest, right? You got to stop, which means your velocity has to stop. Your speed's got to stop, right? So you got to take this velocity function, v of t, which is t cubed minus 3t squared plus 2t, and we got to set that. When does it come to rest? And let's go ahead and factor a t out. And let's solve by factoring. Let me get a little room here as well. Erase all this. And now we have like a testing interval, okay? So t at 0 seconds, the velocity, object is at rest. At 1 second, the object is at rest. And then at 2 seconds, the object is at rest. So 0, 1, 2. So what's it doing in between there? Well, normally I would like test a time of -1, but this is not Back to the Future. We can't have -1 second, so I don't need to worry about testing for negative time. So let's go ahead and plug in like t being a half, 0.5, and I would plug it in, right? So here's my v of t, t minus 1, t minus 2. I'm plugging in a half. So I have a half times negative a half times -3 halves. Well, that's a positive 3/8. All I care about is it's positive. it's positive. So it's moving. So because I have to change direction, meaning if this is up and down, this object's going up from 0 seconds till 1 second. Now I got to see, does it keep going up or does it go down and actually change direction? Right? I need it to change direction is what I'm looking for. So then I throw in, let's throw in 3/2 now, 1.5. Well, this is positive. That's positive. 1.5, that's a negative. So positive times a negative. That's a negative. So it does go down, right? It was going up, but then it went down. So it changed direction at t equals 1. Now the question is, does it change direction after 2? So let's go ahead and test like 3, something out here. 3 would be nice and easy. Let's throw that in. Positive, I have a positive, I have a positive. Okay, I guess it's going back up again, this object, if it's up, down, right? If it's right, left, then it'd be like right, then it's going left, then it's going right, and so on. But the velocity has to change, right? It has to change direction. So it sure does change at 1 second, and it sure does change again at 2 seconds. But the signs have to change, right? So when does the body change direction? At 1 second and at 2 seconds. Okay. If this would have been like plus, 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 then I would have said it never changes direction. It goes up, it stops, keeps going up, stops, keeps going up, right? All right, this time the velocity is given. So find the acceleration. So we have velocity. The acceleration would be that derivative. So 2t minus 4. And find the body's acceleration when the velocity is 0. Well, I don't know when the velocity is 0. Let me go to the side and find when the velocity is 0. When does this thing come to rest? Well, it looks like at 1 and 3, it comes to rest, right? And then what is the body's acceleration at the time that the velocity is 0? So let's go back. Here's our a of t. Here's our acceleration. Let's plug it in at 1. So it looks like at 1 second, I'm -2. This would be like feet per second squared, whatever our units are. Now let's do it for 3 seconds. A of t equals 2t minus 4. So a of 3, 2 times 3 minus 4. So 6 minus 4, I got 2 feet per second squared. There's the acceleration when the velocity is 0. All right, here it says, when's the body moving forward? Well, the body will be moving forward. So this is like, think about maybe right and left instead of up, down now. Forward, backward. Forward would be your velocity is positive, right? So when's your body moving forward? When the velocity is positive. When would it be moving backward? When the velocity is negative, right? So what I'm going to come back to is, first of all, when did I stop? And we solved this above. And this was at 1 second and 3 seconds. So I have a testing interval at 1 and 3. I got to decide what I'm doing in between there. So let's throw in something to the left of 1. Don't throw in 0. Let's throw in like a half, right? t being a half. Maybe we'll throw in like 2 here, and then we'll throw in like 4 here. And remember, this is into t minus 1, t minus 3. So if I throw in a half, I have a half minus 1, a half minus 3. So I got a negative times a negative, which is a positive, right? And then I throw in 2. Well, 2 would have a positive times a negative, which would be a negative. And then I throw in 4. Again, I'm testing it into the velocity function. I throw in 4 seconds. 4 minus 1 times 4 minus 3. That's a positive. Okay, so when is it moving forward? Whenever the velocity is positive. So when am I moving forward? Well, from 0, can't have negative time, right? From 0 up until 1. At 1 second, it stops, so it's not moving forward anymore. But then it moves forward again after 3. At 3 seconds, it stops, but it's positive. Velocity is positive after. So it moves forward after that as well. That's when this thing is moving forward. When am I moving backward? Well, when is my velocity negative? Well, between there. Between 1 and 3 seconds. The body is moving backward. All right, when is the body's velocity increasing? When is the body's velocity increasing? So that would be when your acceleration would be positive, right? You're accelerating. You have positive acceleration. That's when your velocity is increasing. When the acceleration is positive. When are you decreasing? When is the body's velocity decreasing? When the acceleration is negative. Think about like throwing a ball up in the air, right? Yeah, you throw a ball up in the air, it's going in the upward direction, but acceleration is having an impact on that. Your acceleration is negative. The ball, while going up, is decreasing in speed, right? But when the ball's coming down, it's picking up speed, right? The velocity is increasing, the acceleration is negative due to gravity, right? Negative 9.8 meters per second squared, or whatever it is, acceleration is. So again, when is the body's velocity increasing? When your acceleration is positive. All right, so let's go ahead and let's take our, where was our velocity at? Our v of t was t squared minus 4t plus 3. Let's go ahead and find our acceleration, which is that derivative, 2t minus 4. And then let's go ahead and, where is our acceleration? 0. And then we can have a testing interval, so a t equaling 2. So here's our acceleration. I'm going to check around t being 2. 2, that's supposed to be a 2 right there. So let's go ahead and test like 1 and 3. So I throw 1 in. 2 times 1 minus 4. Okay, it's negative. I have negative acceleration, meaning the body's velocity is decreasing, right? And then I'll plug in 3. I got 2 times 3 minus 4. Looks like that's positive acceleration there. So velocity is increasing from 2 and on, right? The acceleration is positive. The velocity is decreasing from negative infinity up to 2. Okay. So again, I would think about a ball going up in the air on that, right? You're throwing a ball up in the air. Even though the velocity is positive, the acceleration is negative on the way up. When it's coming down, velocity is still negative. The signs agree, and the acceleration is negative. Okay, so the signs have to agree, right? But deal with acceleration there. All right, let's keep going. A dynamite blast pulls a heavy rock straight up with a launch velocity. So here's your straight up scenario. This is a good one. How high does the rock go, right? In other words, so, if you're blasting this thing straight up, when does it stop? When's your velocity 0, right? Before it falls back down. So we want to know, when is the velocity 0? Well, if this is your position, your velocity would be 160 minus 32t. When does that equal 0? Add 32t to both sides. At t being, what was that, 5? At 5 seconds. T being 5, right? In fact, if you were graphing this position function, here's our position function in blue. It's kind of like this, right? It's going to reach its max height after 5 seconds. I'm graphing the position function, not the velocity here. Graphing the position function, right? Well, how high does it go? Well, that only tells me that it stops at its peak at 5 seconds. What's its actual height? Well, I got to go back to the position. S of 5. So I got to plug 160 times 5 minus 16 times 5 squared. And let's see, 400 feet there. All right, what's the velocity of the rock when it is 256 feet at a height of 256 above the ground on the way up and then on the way down? Well, if it's 256 feet above I don't know at what seconds that happens, right? 256. That's what I gotta solve here. Let me add 16t to, let me get everything on the left-hand side. Let me factor a 16 out. Let's find, when is this height? $256 feet. It looks like it happens at 8 seconds and 2 seconds. So like back to our picture, at it hits this at 2 seconds it happens, and over here at 8 seconds it also happens to hit 256 feet high. This is the position function that I'm graphing, right? Something like that, obviously not drawn to scale. Okay. And so this means that the rock is, well, I guess the next question is it moving up or is it on the way down? Well, remember, velocity tells us the direction, right? So if I throw it into the velocity function, the velocity was 160 minus 32t. If I throw it in, so I got 160 minus 64. I'm like, oh, that's positive. It's on the way up. Right, you can see it. Oh, it's on the way up. If you plug in 8, at the 8 second mark, it'll be on the way down. 32 times 8, 256. I got 160 minus 256. That's a negative value. So it's on its way down, right? The object at 8 seconds. So that's on the way up, that's on the way down. Both of them are at the same height. Let's see, and let's go ahead and answer this of what it is. What is the velocity when it's 256 feet above the ground? 96, and this would be feet per second. Over here we got 256 minus 160. And it looks like we're negative 96 feet per second over here. Would be our solution on that one. So this one's a positive on the way up. This one at 8 seconds is on the way down, negative 96 feet per second. They happen to have the same speed, right? Both the same speed, even though they're going different directions. All right, C and D. What is the acceleration of the rock at any time during its flight? Well, our velocity function was 160 minus 32t. So if we go ahead and find the acceleration, which is that derivative 160, 0 minus 32 times 1, so negative 32, and this will be like feet per second squared. So it doesn't matter what your time is. Notice there's no t anymore. The acceleration at any time is negative 32 feet per second squared. Yeah. When does the rock hit the ground again? When does it hit the ground? Well, here's our position function. When does it hit the ground? When is your position 0, right? When you hit the ground, you're at a height of 0. Let me take a 16t out. So I'd have t being 0, I'd have t being 10. So, and notice it says, when does it hit the ground again? Right, again. It got launched from the ground at 0 seconds. It's going to hit the ground again 10 seconds later. And I hope you found this interesting, our little discussion on rates of change with our derivatives. Thanks so much for watching. See you next time.